have Adam Moravansky. Did I get your last name correct?
Yes, Moravansky. Yes.
Great. Okay, so Adam, first, thank you for joining us. I know you made some accommodations for your time zone. We very much appreciate it. So Adam's Senior Director for Simulation Technology at NVIDIA. He's creator of the game physics engine NVODE-X, which we now know today as NVIDIA PhysX. And many of you know I went to grad school for graphics at University of Pennsylvania. And that, when I was learning about graphics, learning about physics, NVIDIA PhysX was the standard. And then when I was teaching GPU programming, I would always use the latest NVIDIA PhysX demo. I especially remember using the supersonic sled to inspire the students. And today, Adam is going to talk about USD physics, which I think is a great topic for us because physics is an area that we're interested in terms of facilitating conversations around standards. So Adam, over to you. I'll stop the share and you can pick it up.
All right, so let me, okay, hold on. There's a button here for share. Yes, okay, screen, maybe this and then share. Can you guys see this?
It looks like it's coming.
So yeah, nice to meet everybody. I'm Adam. I'm responsible right now for a real-time simulation at NVIDIA, and in particular in Omniverse, which is our big project. I'm sure you guys have heard about it already. And I'm going to be quick because I have relatively many slides. I'm also going to guess that you, oh, by the way, do you see this? Like, this is like the video of everybody. I probably should like make that go away unless it's like, is there like a piece of my screen blocked by like cameras? No, it's okay.
No, it's just you. I think we just have
all right. Okay, good. So basically, I think you guys have heard about Pixar's USD. It's this open scene description platform for content creation, and it's really powerful and amazing. And while the original focus of it is graphics, already relatively soon, we at NVIDIA got together with Pixar and Apple in an effort to extend USD with the ability to also describe physics simulation, and in particular, real-time rigid body simulations. We have a big vision for being able to do all sorts of physics, but we wanted to start small and find common ground. And Apple was already doing a kind of bespoke schema extension for their augmented reality platform and simulation within that. And so they were interested. And of course, Pixar is also relatively big on simulation and understands it quite well. So we thought that would be a good place to start. So this is the whole history of the operation. We have at NVIDIA started looking at USD in like end of 2017. And then already a year later, we started this collaboration with Pixar and Apple to add physics. Then 1 year after that, NVIDIA Omniverse went into the first public beta release. And then it took quite a while. It was only in June 2021 when Pixar published the fruit of our labor, this first USD physics extension spec to USD, which is now part of the USD repository. And since then, we've been having regular bi-weekly meetings of this working group, which has extended, like you guys have apparently also been, like I've seen in the Material X presentation, similar deal, similar collaboration. Now we have Apple, Adobe, Algorix, Microsoft, NVIDIA, of course, Pixar, Side Effects, and Veta on board. So it's quite exciting, and I believe it's gaining momentum. Everybody is, if you guys think that this is after my talk, if you believe that for your company this is interesting, then by all means reach out, and I can ask Pixar to invite you. Officially, it is organized by Pixar, but at the same time, it's not a very formal operation. Let me go here. This is NVIDIA's USD Innovation Process, and This is also very informal, but it's what works for us right now. So it's not only our hardware that's very parallel, also our company is very parallel, and we have a lot of teams working at the same time on many different things, and it's often chaotic. So often two teams discover that they're working on similar things, and then they realize that you know, they need to work together. Even more important than that, one thing that's important with Omniverse is that it's really a USD native platform. So as opposed to almost every other tool, we don't have our own native data representation. If you want to express anything in Omniverse, you have to be able to express it in USD. So far further in our kind of creative process, let's say, we have to think of USD, because as soon as we want to like be able to just like you know, reason or serialize anything, we want to have a USD schema for it. So very early bespoke schemas get created all the time, and then we kind of, as we iterate on them and as they mature and teams compare their nodes, an internal version gets created along with an internal implementation. And then once we believe that we're sufficiently sure about what we want to do to bring it in front of this working group, then we propose it there. Then the working group iterates further, and of course all the different companies also give their angle, and then eventually the hope is that a standard gets created that we can publish, and then already, because we've been iterating on our implementation of this the whole time, hopefully not with a great deal of delay, we also have an implementation working. Another key part of our process is that our physics engine, PhysX, which you have briefly mentioned earlier, has now become open source with the latest version. And the reason for that is so that just like with Material X, it was mentioned that it's very important to have an open source editor, like node graph editor. In that case, we believe it's very important for USD Physics to have an open source implementation. And therefore, right now, our CPU implementation, which is the only implementation of USD Physics that I'm aware of that's available, is available for free on GitHub with full CPU source. Oh yeah, maybe I show this quick video over here. I don't know how well the video comes across, but this is like one little mechanism that we did in Omniverse that I think is quite cool. So this is like a woodworking kit that you can download from this guy's website, DerekHugger.com or something like that. So he makes these mechanisms that you can really make out of wood, and like you know, little cams and so on that you cut out, and then you add an electric motor, and then it's going to basically create this like kinetic sculpture. And we thought that was so cool. We recreated a digital twin of it in Omniverse, and it's all described using USD Physics. So it shows you what you can do with USD Physics. Okay, so really quickly, let me see, where am I doing? Because there is quite some time pressure. Okay, I think we're kind of still good. We're going to have less questions than we were hoping for. USD Physics is super simple, and the guiding principle is that we only put things in there that are either absolutely necessary or it has some kind of real life physical foundation. So there is basically a physics scene, which is a new USD prim, if you're familiar with USD, that basically specifies what kind of gravity you have. And then in the USD metadata, you have things like, you know, what are your units compared to meters. This is like standard USD, but we extend that with like kilograms per unit, which lets you have basically where we introduce mass units, which is important for simulation. And then you can then, this is also very important because of course it's this thing about how the spec is always starting with something that's like kind of let's say proprietary or like hasn't been standardized yet. It's all sorts of properties that are practically necessary to have a physics simulation, but is maybe like, let's say, PhysX specific. We don't want to make USD Physics PhysX specific. We want it to work on every kind of physics engine or as many as possible, right? And they are actually very similar in general, the different real-time physics engines, but these properties are PhysX specific. So they're not part of the physics scene class, but they're like custom attributes that are like in here in this PhysX namespace, but you can basically add them, and then you can basically do all kinds of obscure things with physics, but still have it be written into your USD file that other physics engines, let's say, will ignore. These are like implementation details. Okay, So then the first thing you want to do is like mark up your scene with like, you know, what different things should collide in the world, right? So in USD, you have meshes, like this is your static ground plane. You can mark it up with an API schema. So it's basically like you can tag it as being a physics collider. And then you can then toggle whether that collider is enabled. You can assign it to a physics scene. So this is basically like a relationship or reference to a physics scene. And that's pretty much it. And starting at that point, that this mesh is going to start to participate in physics simulation. Then you can define rigid bodies. It's the same idea. You already have like an X form. You tag it, say that it's a rigid body. You can add optional mass properties. That way you can now have access to these attributes, like it's just mass properties, like you know, principal axis, diagonal inertia, mass, density, usually optional. So you can decide whether you want to, for example, specify the mass or the density, or you want to derive this from the material. So all of these things are optional. You can also, for the collider, that is like a child mesh, for example, say that you want a convex Hull approximation. So I'm not going to go into a lot of detail here, but we have support for materials. That's also, if you're extending the graphics material. You don't have to extend the graphics material, but you can with additional physics properties like the static and the dynamic friction coefficients. And that will then basically guide how the rigid bodies and then colliders are going to interact with each other. You can then also introduce joints like this revolute or hinge joint, where it's a new prim. This one is not just hanging, like adding an API to something. It's a whole new object. You have basically the joint frames, and you reference the two different bodies that you want to join together. You can make it breakable. You can limit the arc of rotation, that kind of stuff. So that's in a nutshell the kind of capabilities that USD Physics gives you. Then, of course, now with the working group, we're starting to discuss deformables, or actually we've been discussing them for a couple of months now. We already have a first proposal. It's still very early, so we're still doing a lot of iteration on it, but it's basically going to maintain this material-centric approach. So basically you can just tag like a material with like deformable properties, and then if you apply that material to like a deformable object, then you can specify like Young's modulus and Poisson ratio, that kind of stuff. There's also extensions for sheets and curves, so you can do things like cloth or hair. And we're trying to continue to focus predominantly on describing real-world properties and no implementation specific details, unless we really have to, because otherwise it's very difficult to make an implementation. So there's always the balancing act there to make it easy to implement. Okay, and then the future area, yeah.
Play the video, man.
Oh, the video. Okay, you would like to see the video. All right. So this is an early scene that we made again inside Omniverse, showing rigid glasses with liquid in the glass and being gripped by like a soft hand, that like soft tissue hand that has like a rigid skeleton inside, and there is some fluid dynamics fire going on. And this is also all described with USD, though only the rigid bodies are now with the standard USD, because we don't have standard USD for anything else yet. But the goal is that you will be able to at some point have completely standard portable USD to describe a simulation like this. Okay. So yes, what do that seeks here, like what do we want to be able to describe in the future? There's a lot of interest in doing like events and sensors and forces and more different kinds of actuators. You can already actuate the joints that you have to like make walking robots and stuff like that, but we want to do more of that. We want to do animated characters and being able to put all kinds of simulated stuff on animated characters. That's like a big construction site in USD, because fundamentally it doesn't have great support for animated characters to begin with, even in the graphics area. then like we don't like right now we have like a spec that would let you do cloth, but we want to do clothing, and that's a big difference. We want to not just be able to do deformables, we want to do muscles. We don't just want to do strands, we want to do like hair that can be groomed, and that's like a big like lots of cans of worms to add the kind of artistic control knobs to those kind of things so that it's really usable. So there's still like a long many years road ahead, I believe. Physics also for solid modeling, so things that you would find in CAD. And then there's also a great deal of interest in non-uniform simulation materials. Like simulation materials are way behind the kind of expressiveness of materials in graphics that we have with Material X. So there's like huge amount of stuff that you can do with defining exactly how a material should look graphically, but doing that kind of thing for physics, like that's not reality yet at all. I mean, even in terms of the implementations that are available. So there's a lot of potential work there. Okay, so important resources, and I have more videos after this if we have time, but I want to maybe give you guys the time that we have for questions. Maybe I can play the videos as we discuss questions. The user's guide for USD Physics is here as part of the regular Pixar USD documentation. The source code is, of course, also unsurprisingly part of the GitHub Pixar USD source tree. And in particular, the most important file is the schema file over here. I think Patrick said that he's going to distribute these slides to you guys, and then you have the links there. Okay, and that's pretty much it. I have a bunch of videos to show like what we have done with this stuff at NVIDIA, but we only have like yeah, I have a hard stop like in 6 minutes. So yeah, if you guys have questions.
Adam, that was really, really awesome, really inspiring, a great breadth intro. I mean, thank you for your contributions to the field. We're always thinking about how do we get to the point where we can do interoperable, fully stimulated 3D worlds. And I kind of feel like I'm looking at the future here with this. So with that said, I'm sure you have a lot of questions in the next 6 minutes. So let me hand it over. I see a hand up for College of Coastal. I just don't see the full name yet.
Yes, hello everyone. This is Herman. Adam, thank you for that presentation. Adam, the question to you is, do you envision the additional physics properties being implemented as layers? So for example, if one of the properties is going to be mass, then if we want to add, for example, electromagnetism, so then we add the layer for electromagnetism, and now one of the properties of the object is going to be charged, and then instead of just having gravity, then we can create electrical and magnetic fields and so on. And then
yes.
I mean, I'm seeing
yes.
that, for example, when we have implemented just curves in the air for just like a ball in baseball, we have had to add the Magnus effect on our own to the engine. And so it will be great to see that as layers.
Yes, absolutely. So this is actually really hard to do, but like one of the main like selling points of USD is this amazingly powerful layer composition technology. And we absolutely wanted to take advantage of that. So these cars that you're seeing, they've been modeled with physics. So we have an artist was creating and iterating on the mesh. And at the same time, like a technical guy was rigging it for physics, and the physics rigging was going in a separate layer, and it's tricky to make. Like in Omniverse, we have had a lot of challenges trying to make it work so that you can put the physics stuff in a layer, but at the same time, yes, we absolutely believe this is super important that you can do that, and we're doing everything that we can to make that possible. So yes, I totally agree. That's super important.
Awesome, thank you.
So yeah, this video I'm showing is like a very produced and post-processed version of a real-time simulation with physics. So obviously you have all the fancy camera cuts and everything that we were using for one of our like GTC demos. And then in the next video, I'm going to show you guys what it looks like kind of raw without any kind of editing, actually with somebody like driving these things real-time with a game controller.
And Adam, there's also a question in chat from Nick.
Mm-hmm. Okay, let's see. Can you read it? I don't see it.
Did you say that an implementation of USD Physics with source code is available for PhysX using PhysX.
Okay, this is a complicated question. There's a multi-part question. So the USD Physics source code is part of the USD GitHub, which is basically like how to parse the information from USD. Now, the implementation, the simulation implementation inside PhysX is also open source. There is a bit of glue code that goes from like between the USD and between PhysX, which is Omniverse source code, which we would like to open source, but it's still in flight and it hasn't happened yet. So there is like one bit of code, which is basically just taking things out of USD and pushing them into PhysX, which is just basically administration, but that hasn't been open source yet, but we absolutely intend to open source it.
Hey, thank you.
Okay. So, this page. Okay, this is the raw video of that same thing. So this is just like driving around with a game controller. Okay, that was kind of short. Go on with questions if you still have them. Otherwise, I'm going to show you this. This is like the non-gamey, more serious application. This is super cool. This is like a collaboration with the ETH Zurich, the technical school, also where I studied, and in particular the robotics group there. They have this quadruped robot called the Animal, and recently they even mounted wheels on the legs, so it can not only walk, but it can also roll. In fact, it can balance on not only 4 legs, but also 2 legs. So it can just suddenly stand up like this. And of course, you can't really program a behavior like this explicitly. You train these things with deep reinforcement learning. And this guy was fully trained in simulation to be able to do this in NVIDIA Omniverse using the simulated PhysX-based USD Physics environment. So later on, let me just go ahead. Okay, here it's going to start showing the Isaac Jim simulation environment in Omniverse, where in just some minutes, I think the full training until full robustness, it goes like not much more than a half an hour, and it's able to then perform like stair climb, stair descent, and all these other behaviors by just like having lots and lots of robots training in real time in parallel. So yeah, you can definitely also use it for serious things. And I was totally blown away that you can just train something like this fully in simulation, and then you don't need to do anything in the real world anymore. You just like put the neural network into the robot and it will just do its thing.
I'm waiting for the robot to run over the kids over there.
Yeah. So the high level behavior in this demo, it's still being remote controlled, but it's basically at the level where you can like press a button and it's going to stand up, like, press another button, it's going to go back on 4 wheels, and you can just drive it around. Okay, let's see. I think that was it for my video. So thank you very much. And I think we are just about out of time. Exactly 1 minute over. So yeah, I now need to go and put my kids to bed so they can get up in time for school tomorrow.